or 4-pi system, and we left off a conjugated 4-pi system. That was the catch, was that the system had to be conjugated. That was the only way to think about all the orbitals overlapping and going from 4 atomic orbitals to 4 different molecular orbitals. And then we talked about standing wave theory, and we also talked about how the molecular orbital diagram was based on this particle wave duality, where you have electrons have some qualities or characteristics of waves and then also particles. So we're able to do that. We showed each orbital and in each harmonic where energy was increasing going from bottom to top. Let me see if I can edit this. So energy is always going to be increasing in this direction. All right. So, and then we also talked about which orbital was the Homo and which orbital was the the lumo. And so with that being said about what we know about conjugation, we're going to start talking now about the first reaction. And I'm going to shuffle this around a bit. So give me a second to move the pages. I want to shuffle this around a little bit. Yeah. So I want to cover cycloaddition first and then come back to addition of HX. All right. So the first reaction that we're going to look at is cycloaddition. So I gave you kind of an overview of that, but I want to give a little bit more detail about the mechanism and things like that before we go into talking about the actual reaction. All right. What's today? 14. So today we're going to start out talking about cycloaddition. You'll also hear me refer to this as a 4+2 cycloaddition or a Diels-Alder cycloaddition. Right, and this is a reaction between a conjugated diene right, and a dienophile. So we're gonna just make this some alkene. Actually, I'm gonna go ahead and introduce it like this. That'll help. We can cover a couple of more concepts and kill 2 birds with 1 stone. Right. So the diene is here. This is my 4-pi system. And what it reacts with in this reaction is what we call the dienophile. Dieno meaning diene, and then phile from the Greek word philos for love, so lover of diene. So you got a diene and a dienophile, and this is going to be my 2-pi system. So that's where the the description 4+2 comes from. It's a 4-pi system reacting with a 2-pi system. All right. So there's some characteristics about the reaction that we're going to talk about at the same time that we're actually talking about the mechanism and all this stuff. So you have to run this under thermal conditions. So you heat it up. So we'll put the delta over the arrow. Sorry about that. And when you heat this up, right, let's just talk about the mechanism. So with the 4-pi system, you have, and I'm going to number this too, because normally whenever I teach this part, it always seems to help when the carbons are numbered. Right. So what happens in this case, the mechanism wise, is we're going to share a pair of electrons here from that pi bond. So you're going to get a bond here between 4 and 5. Right. And then that pair of electrons here is going to get shared. Like so. So you're going to get a bond between 1 and 6. And the numbering is arbitrary. It's not, you can number it however you want, but the point is that these two atoms right here and these two atoms right here are going to have a bond between them. And then the last arrow in the mechanism is here, where that pi bond gets shifted over. So you end up with a new bond between 2 and 3, a new pi bond. All right, any questions about that so far? So you have, let me fix that out, that pi bond down there. It's kind of sloppy. Right, so you have your 4-pi system reacting with your 2-pi system, and the arrows are the same. The mechanism is what we call pericyclic. And what that means is that the electrons move kind of in a circuit over only specific atoms in the arrangement. Right, so only these atoms are involved, right? And you can see the 6 atoms that are here. Any substituents or anything like that, they don't get involved in the actual reaction. And you can also see that this is setting us up for the formation of a 6-member ring, right? So the final product is going to look like this. Let me just draw the ring out. All right, so that's my 6-member ring, and then my double bond is going to be here. And then the two groups. So let's go ahead and put the numbers back in. This is 1, that's 2, that's 3, that's 4, this is 5, and this is 6. So those groups on 5 and 6 right? How are they arranged in the star material? Like when you look at the alkene, the dienophile, are those 2 methyl groups cis or trans?
No question.
Go ahead.
Why did you switch the 5 and the 6 for the
Oh, sorry. Yeah, my bad. That should be the same. So 5 is at the bottom. My bad. So what's the arrangement of the 2 groups over in the dienophile? Cis or trans?
Trans.
Good. They're trans. So in the product, well, no, I don't. In the product, they also have to be trans. That's one of the key characteristics of this reaction. This is going to be here, and then the other one will be here. Let me zoom, move that so I can write some notes in here. Right, so I'm gonna highlight the substituents in a different color. Right, so the substituents are, let's see, so the substituents are trans in the dienophile. They also have to be trans in the product. Right, so they have to be trans in the product. That's one of the characteristics of the reaction. We say that the reaction is what we call stereospecific. That's the term for that. So stereospecific. What that all that means is that the stereochemistry of the dienophile is maintained. So the stereochemistry of the dienophile is maintained in the product. So if your dienophile is trans, the groups and on the ring and the product are going to be trans. If it's cis, the groups are going to be cis. But that's one of the key characteristics of the Diels-Alder cycloaddition is that it's stereospecific. Right. There's a reason for that, which we're going to talk about in a second. But does anybody have any questions about how the ring got formed, the arrows that got pushed, anything like that, before we start talking about in more detail about the mechanism itself? All right, so we know that it's a pericyclic reaction. We know that it's stereospecific. There's a way to speed the reaction up, and we're going to talk about that. But first, we got to talk about what's happening in the actual mechanism, like what's reacting. So that's why we did the molecular orbital diagrams first, right? So we know what the molecular orbital diagram looks like for that 4-pi system. We also know what it looks like for a 2-pi system, right? So with that being said, let's talk about how the reaction actually happens. Right. So in any 4+2 cycloaddition, it is an interaction between the Homo so the Homo of the diene is going to overlap with the lumo of the dienophile. right? So the HOMO of the diene overlaps with the LUMO of the dienophile, and that is how the reaction happens. All of the bonds that are formed and things like that, all that happens because of orbital overlap. So the orbitals of the diene, the HOMO, overlap with the LUMO of the dienophile, right? So if it's the HOMO that's overlapping with the LUMO, it's the HOMO that's supplying the electrons to initiate the reaction. Because when we look at the HOMO of the diene, which is here, right? It has a pair of electrons in it to donate. And if you look at the LUMO of the dienophile, which is here, it's empty. And that matters, right? So when we talk about HOMO, LUMO overlap, let me go back to here. So the HOMO is filled and the LUMO is empty. Right, and that actually matters, right? So the HOMO is going to be, in a sense, is going to be like your nucleophile, and the LUMO is like your electrophile. So the way this works, if we look at the HOMO, and then we're going to talk about a couple of other pieces of information related to this idea as well. So we look at the HOMO. Look at the HOMO, which is here. Put the orbitals in. Right, and again, the HOMO looks like this. I'm gonna shade these, and I'll shade these, because if you look at the HOMO up here, you can see that there's one node between and it's symmetrical. So you got two orbitals on the left, two p orbitals on the left, two on the right, and the sign changes because of that one node. I'm sorry. So this is what the HOMO looks like. Everybody agree with that? Anybody disagree?
I agree.
All right, and then so this is the HOMO of the diene.
I have a question.
Go ahead.
For the HOMO of the diene, does it matter where we draw the pi bonds, or
I'm not sure if I understand that.
like the?
Go ahead.
Go ahead.
No, go ahead. I want to hear your explanation, because I'm not sure
Yeah.
if I'm
Like on
understanding.
the alkenes, like, does it matter where we draw that second line?
Where else would you put it? Would you want to put it here?
No, like, no.
Yes,
No.
I'll say, you can't do that now.
Yeah, but like on top of the line.
Oh, no. So you're saying to draw it here
Yes.
like that? No, that's symmetrical, so it wouldn't matter. That doesn't change anything.
Okay.
Yeah, that doesn't change anything. All right, so that's the HOMO of the diene. This is the dienophile and the LUMO. So if you recall, the LUMO it has one node between those two orbitals. So it has one node here. Now, I'm just asking this. You may or may not catch it, but I want to see how you're thinking. How should I shade these orbitals? What do you think? How should I shade them? If I want to overlap them and make bonds between the atoms, how should I shade the orbitals?
Would you shade one of them at like the top and then the other one at the bottom?
Yeah, that's a given because of the node. But which one would you shade the top part of? You're right. You're 100% correct. Which one would you shade the top? Which side? The left side or the right side?
The left side?
Right here?
No, yeah, left side.
That, like that?
Yeah.
Okay. and then you'll do this here. Is that right?
Yes.
Okay. That I'm glad you answered it that way. All right, because that gives me an opportunity to explain another part of this. When you're overlapping orbitals, remember the orbital itself is an equation, right? We talked about that on, well, the Friday before we left for spring break. We talked about how the orbital, the p orbital itself, is an equation of the path of the electron around the nucleus of an atom, a given atom, and there's a node between the two orbitals, and so one of them is shaded and the other one is unshaded. The shading represents the sign. Doesn't matter if it's positive or negative, but the sign changes because of that node that's right here. So the shading is indicative of the sign of the equation, right? And so if that sign, and think about this, if I wanted to add something together, I would want the equations to have the same signs, right? So if I want to overlap these orbitals, what we call constructively, I need these two things to have the same sign. Right now, they don't. This would be if if I try to overlap a shaded orbital with an unshaded orbital, they'll cancel each other out. Right? This is what we call destructive overlap. So they're going to cancel. So I actually need the lumo. I need the signs to line up. So I need this to be unshaded. And I need this to be shaded so it can overlap with that. Right? So the signs have to be the same. I'm just going to use shading because we've been kind of making those two synonymous. So the signs have to be the same for proper overlap.
I have a question.
Go ahead.
Could you go back to what you were just explaining about the signs, like the destructive overlap?
Yeah.
Can you re-explain that, because I don't understand?
Okay, let me ask you, let me just say this. So the lobes are all the same size, right? So that means that the value is equivalent. As a part of the equation, the value of each lobe is going to be equivalent. There's nothing to indicate that the lobes have different values, because a p orbital is symmetrical. And even though my drawings are kind of crappy, the lobes themselves have the same size and the same if we give it a numerical value, they're going to have the same numerical value, right? So if I look at these two orbitals, and let's say that this one is, let's say just for the sake of argument, that each lobe is +1 or -1. All right. So we're going to say, let's say the shaded is +1 and the unshaded is -1. And this is +1 and this is -1. When I take +1 and -1 and put them together, or try to overlap them, I'm going to get 0. Is that right?
Yes.
So when those signs are different, but they have the same value, they're going to cancel each other. So that's why you have to have the orbitals have to have the same signs in order for you to get what we call constructive overlap. So that's what this is. let me change the color. So these orbitals have the same signs. So it's going to be constructive overlap. All right. Does that make sense now?
I get the destructive overlap, but I don't understand like how they have the same sign for the constructive overlap.
Oh yeah. So here again, if this is +1 This is -1. Unshaded is minus and shaded is plus. This is going to be -1. And this is going to be +1. So when I add the two together, -1 and -1, they don't cancel. They actually combine, right?
Okay.
Does that make sense?
Yes.
Yeah. So because think about it, the actual orbital itself is not a real thing. It's an equation. It's a graph of an equation. And so if you do, let's say you do draw a graph on the Cartesian plane, right? And you got a graph of some weird uh equation that has like that's like that has a square in it or something like that, and your graph looks something like this, right? This part of the graph is going to be what? Positive, because it's on the top side, right? These are positive y values, and over here positive x values, and then anything below 0 on the axis here is going to be what?
Negative.
Negative. So it's the same idea. If you have a p orbital, anything, right, and that node is there, depending on which way it's facing, because you can have a p orbital on either the x, the y, or the z axis, but that's beside the point. Though the sign of that equation is going to change because of that node, right? So the node represents a place where the equation passes through 0. So the
Okay.
sign is going to change based on when that node is there. Whatever is above it is going to have the opposite sign of whatever is below it.
Okay.
And I'm not saying it has to be, the top has to be positive and the bottom has to be negative. All I'm saying is that the lobes have opposite signs because of that node.
Okay.
Now, I'll write that in here. Right. So because of that node, you're going to have opposite signs. So the point is, anytime you want to overlap orbitals to form a bond, they got to have the same sign. That's the bottom line. So when I bring in the lumo has to match the HOMO in the sense that if I want to overlap these two orbitals right here, they both need to be shaded. If I want to overlap these two, they both need to be unshaded in order to get what we call constructive overlap.
Oh.
That's the bottom line. I know we went around the world to answer that, but it's good because all the more information you know, the better it is when you see this somewhere else, and you can pull all that information up to get to that, that final conclusion. So it's good. All right. So the Homo lumo overlap is important. The amount of overlap is going to be based on how well those orbitals are able, how close they are able to get to each other, what the gap is, the energy gap, excuse me, between the Homo and the lumo. All that stuff matters. All right. So with that being said, there's a couple of things we need to know about the structure of the dienophile as it relates to overlapping with the lumo of the diene, because there's a stereochemical requirement for your diene that has to be met. Otherwise, it won't be able to overlap properly. So let me show you that. And I think I'm gonna change colors. Let's put a line. So in order to achieve proper orbital overlap, you got that there's a specific conformation that your diene has to adopt. And I'll zoom out on this. It's easier for me to write when I zoom in. So in order to achieve proper orbital overlap, your diene must be what we call S-cis. It must be in the S-cis conformation. And I'll show you exactly what that means. Give you a chance to write that down. So in order for your diene, in order to achieve proper orbital overlap, the diene must be S-cis. That's a stereochemical conformation. Right, so this is what the diene looks like. Right, and this is S cis, where both pi bonds are on the same side of the sigma bond. Can y'all see that? So this is my sigma bond right here. S cis means both pi bonds are pointed in the same direction. Right. This is part of the reason why you have to add energy. You have to heat this reaction to get it to go, because the preferred conformation for the diene is not S cis. It is, right. This is what we would call the STrans conformation. All right. Mr. STrans, why do you think that's the preferred conformation? What do we know about atoms and electrons and as far as them wanting to be near one another, close to one another, or is the spacing and the proximity of those things better when they're further apart or when they're closer together?
Is it they want to be further apart so they're like not too sterically hindered?
Yes, that's exactly right. Thank you for that that answer. And that's the exact term that I was getting at, sterics. If it's a sterically hindered system, the energy is going to go way up. And so when you have a system like this, where you can adopt this S-trans conformation, it's going to lower the energy of the system overall. So in order for this to get this to react, and if we were to show these two in equilibrium, the equilibrium would actually favor S-trans, right? So we can draw it that way. That's why when you do a cycloaddition, you can't do it at room temperature, because you need some energy in order to rotate around this bond, because that's what happens. You have to rotate around that bond, and it's not free rotation, right? But it costs a little bit of energy, but it can happen if you increase the energy of the system. So that's how you go interconvert between S cis and S trans. You would rotate around the bond to get to S trans. Right. So, and that's a steric argument. That's why you have to heat it up. So you have enough energy to get that rotation between S cis and S trans. And then once it's in S cis, the reaction happens and then it's irreversible after that. So yeah, so this is another key characteristic of the Diels-Alder. So we know that it's stereospecific. We also know that the the diene has to be S cis in order for it to overlap. And if you think about this in terms of the transition state, which is what we were talking about here, I didn't make that clear, but this is what the transition state looks like. Right, when you think about that S trans diene trying to react, if it's like this, and then you have a dienophile here like this, this side is fine, right? No problem. Right here is where you're going to have a problem, because the orbitals are going to be too far apart to interact. Right, so if those orbitals are too far apart, they're not going to overlap properly. So this is why the S cis is preferred. this is, yeah, I'm gonna write that in here, S. So a 4 plus 2 it can't occur if the diene is STrans. Right. So you can try, you can, if you have a, and there's some specific cases where this matters, right? And it only happens if the diene is locked in that type of conformation. We got a couple of examples that I think down here somewhere where we'll talk about that. But it only if it's locked in the STrans conformation will it not happen. And there are some cases where you can only have a diene in STrans, but we'll talk. I don't want to. Well, I got time. I got 4 minutes. I'll go ahead and show you, and then we'll stop. And then on Wednesday we're going to start doing some of the examples, working through the examples. Right. So let me just put that here. So there are some cases where the STrans is the only possible conformation. So if we have a molecule like this, where my diene is here, right? You can see right away, this is not going to be able to adopt S-cis, right? Because the pi bonds are in the ring. They're part of the ring. And so this is locked. Right, so this will not react. Right, so that's not going to react in a 4 plus 2 because the diene can't adopt the proper conformation. If we have that same ring, that same type of system, but it looks like this instead, where we have this and that, then this is fine. Because you can see the difference, right? The alkenes are both, the pi bonds are both pointed in the same direction. So that can react. But if it's locked, then it can't react. Right? Another example of where STrans will be preferred, and the system will more than likely adopt the STrans and not be able to adopt the S-cis is a system like this, right? Where you have these methyl groups right here, and they want to get away from each other. And so the equilibrium is going to lie way to the other side, and the STrans is going to be the preferred conformation here. Right, and again, this is going to be based on sterics because those methyl groups do not want to be in proximity to each other like that. So this is not going to, this won't happen. Right, so STrans is going to be preferred in that case. So a diene like this is not going to react under Diels-Alder conditions, no matter how much you heat it up. All right. Now, if we take that and take the same type of diene, but change the structure to where the methyl groups are not able to interact like that, and it will react. So something like this, where the methyl groups are here, that can stay S-cis because you don't have that steric interaction, but you have a got a steric interaction between those methyl groups. It's gonna force that bond, force rotation around this bond to get one of those methyl groups out of Dodge. And that STrans conformation is gonna be favored. All right, we're gonna stop here. It's 9:50. And unless there are any questions, we'll stop and pick up on Wednesday.